Hello, welcome to a set of videos that I prepared in the area of mechanical vibrations. And this set of videos will cover the topic of modal analysis. Our aim is to understand modal analysis, what it is. We need to learn what vibration modes are. And we will look at them sort of in an overview type of way for continuous systems. But we will mostly do our work with lump mass systems. So those are the two types of systems that we will cover. In this topic are mode shapes for continuous systems, also for lump mass systems, as we shall see. So mode shapes and modal frequencies, and then the role of each mode in the overall vibration of whatever structure we're looking at. Lump mass systems, we will look at those and actually analyze some of those. They're interesting too. How to get the mode shapes and the modal frequencies in the open source MATLAB-like program Octave. This is an eigen problem, so we will look at how to get our eigenvalues, which then give us what are called our modal frequencies, and then also the shapes of those vibration modes. And then we'll talk about the outcome of what we produce and see how it is useful in the real world. Now, we'll start with continuous systems, like I said, and you can go Google beam mode shapes or something like that if you want to. I did that and I found these drawings on the internet. This is a case of a fixed beam. As you can see, there are fixed moment-bearing supports on either end. And basically what happens with a continuous system like a beam, what I mean by continuous is it's not individual lump masses. We'll see the difference in just a second. But when you excite that beam by hitting it or something like that, it vibrates. And it actually vibrates not with one frequency, it vibrates theoretically with an infinite number of frequencies. But what happens is that the mode shapes, which are shown here, this is how the beam oscillates, diminish in importance as you go up in mode shape. So, for instance, this first mode shape, which is just the beam bending like a sine wave in a way, with one peak, is the fundamental mode, and normally it will be the one that is most easily excited. The second mode shape, it does look really like a whole sine wave here in a way, but you have two peaks in it, and as you go along, what you can see is you get more and more peaks. And then the other thing that's important, so our beam basically is oscillating in all of these mode shapes together. And the oscillation of the beam, the total oscillation of the beam, is the superposition of all these different vibration modes on top of each other. What happens though is that with each mode shape there's a frequency that belongs to that particular mode, and the frequencies go higher and higher and higher. So for instance, this fourth mode shape, the beam is bending a lot. Has a lot of little peaks, and these are called nodes here, where it where it's sitting, that mode is sitting on the equilibrium position of 0. But the amplitude of these vibrations, so the frequency will be high, but the amplitude is very, very small. And oftentimes you can't even perceive that because the amplitude is so small compared with the amplitude of the lower modal frequencies and mode shapes. So again, the way that these look, and we'll see it below with some examples, is that you have less bendy modes. That's not a good word, but I'll use it anyway, for the lower modes. And as you go up in modes, your bending gets to be greater and greater and greater. the frequencies get to be greater and greater and greater, but normally the amplitudes of vibration are less. Now, there's one exception to this, or an important exception to this. If this were just a free system, then we wouldn't need to worry about what I'm getting ready to say. But if you excite a structure at one of its modes, even one of the higher order modes, if you excite it at that modal frequency, then that mode shape can become predominant, and we'll see this also. Or it gets to be more important anyway, where you could neglect it if you were away from that nodal frequency. If you're forcing the system at that nodal frequency, then you may have a problem. Generally, when you have forced systems, you try to design them so that they're away from their modal frequencies, and you're not going to excite those frequencies when the thing is in operation. All right, so this is a fixed beam as I've shown. Here's a cantilever beam, and the same type of principle applies. The modes get more bendy as you go up in mode. So, for instance, the first, so we have a fixed beam, and it's fixed over on this end. It's just a cantilever beam, and the first mode is simply this kind of wagging back and forth. This is shown in one position, but it comes down, and you have it oscillates between the mirror position on the bottom and the upper position shown here. We only have one antinode, as they're called. If you're on the equilibrium position, you have a node. So that would be a node right there because it's fixed. If you're away from that, you have what's called an antinode. So anyway, we have one antinode here, and here we have two antinodes. We have the original node over here on the left, and then we have this node here where the beam passes through there. But we have two antinodes. So we have a node, we have two antinodes, that one there and that one there. If we keep going down, one node, two nodes, three nodes, one antinode, two antinodes, three antinodes. So it looks like every time you go up in mode shape, you have another node or antinode. I was calling this bendy before, but that's probably a more, the way I just described it is a more scientific way to describe it. And again, this frequency will be lower than the second natural frequency and third natural frequency. This is only showing three modes. Again, there's an infinite number of modes theoretically, but normally, like I said, once you get past 3 or 4 modes, the severity of vibration with the higher order modes is less and less and less. So typically you look at the first few modes and then you just forget about the ones after that. All right, now for real systems, here's a ship, and a ship is really like a beam. In fact, a ship is a very interesting beam because it's not fixed to anything. It's not a cantilever beam, and it's not a simply supported beam. It's just a floating beam in a liquid medium, so it actually can has a lot of freedom to move. This would be the first bending mode of this ship, because again, you have one big antinode in the middle, or let's just say that. Let's leave it at that. This is a torsional mode, okay, which you often don't think about, especially if you're doing simple analyses like these. But physical structure can be twisted also, and you do have torsional modes. So this shows the torsional mode of the ship. These are arrived at, actually, you can see the little mesh here with finite element analysis. Here is a higher order mode of vibration, and as you can see, we have a lot of nodes and antinodes here. So the ship really is, it's in bending, but it really is wiggling here. Okay, this is a C-130 airplane, which is an American transport aircraft, but also cargo aircraft. Very famous. Has 4 propellers, but Its first mode of vibration is the wings flapping, basically. The wings, it's like the, actually the cantilever beam, if you recall. Let's go back up and look at that real quick. This mode right here where the wings are flapping up and down. So that is our first mode, flapping wings. Second mode is it's another bending mode for the wings. Okay, and as you can see, it's like that second mode that we saw for a cantilever beam. That's the reason that we study these simple cases, because they are translatable to more complicated structures. Okay, and so that makes sense. I'm going to stop real soon for this first video, but when you get on up, so there's lots of different mode shapes, and you can look these up on Google if you feel like it, the C130 mode shapes. I think they give 10 altogether, but as you can see, like we saw before, you get really crazy modes when you go higher up. Here you have your horizontal stabilizers flapping up and down. Your beam, your wing is actually, it has multiple nodes and antinodes. But like I said, so this will be a higher order mode. The frequencies will be higher and the amplitudes generally are less. But obviously they've analyzed this, so they're not saying, hey, this isn't important after mode 3, we can just stop here. They continue. And then you get a real crazy mode here. Look at this one for mode shape 10. This is a torsional mode for the wings, as you can see. And then you have some weird stuff. This looks like actually the second order cantilever beam here. And then this is cantilever beam here, the vertical stabilizer. Okay, I'm going to stop here and start over again at this point in just a minute.